This is Joanne with Read Science. We are here, and I'm here today, of course, with my co-host, Jeff Schomeyer. We have today with us a pair of co-authors, and they're a great team because they've put a lot of books together. Let's start with their newest. Their first book is Magnitude, the Scale of the Universe, and this one is recent. Their previous one was a book called Light. I'm going to lose my headphones. Light, the Visible Spectrum and Beyond. And these are two great picture books. And then one that's a little more, well, it's got pictures, but more text heavy is Your Ticket to the Universe, a guide to exploring the cosmos. I hear this is not how the cover should look. But we welcome today Kimberly Arcand and Megan Watzke. You guys say hi.
Hello.
Hi, everyone.
Yeah.
Starting, Megan Watzke likes to share, and I'm quoting from her, the wonders of science with the widest possible audience, which is what we really like to hear at Read Science. She has a bachelor's degree in astronomy and astrophysics from the University of Michigan, the master's degree in science journalism from Boston University. She's been a public affairs specialist for the Harvard-Smithsonian Center for Astrophysics, and also the press officer for NASA's Chandra X-ray Observatory. Here at Read Science, where science communication is our thing, we're always happy to talk with people who write, and I'm quoting again, Megan sees endless opportunities moving forward to improve the connection that people have with science. Welcome, Megan.
Thank you very much. Glad to be here.
Yes, Jeff, you always do the introduction so much nicer than I do. Sorry, Kim. Okay, so Kimberly Arcand is the visualization lead for NASA's Chandra X-ray Observatory, which has its headquarters in Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. You're an award-winning producer and director, it says here, and a leading expert in studying the perception and comprehension of high-energy data visualization across the novice to expert spectrum. So what I'm very excited about is the fact that you were a molecular biologist before this, and you've been able to bring those skills to space study and exploration and explanation. Welcome. We're so glad you could come.
Thanks. Yeah, I'm really excited to be here.
And we let Jeff throw out the first question.
Oh, I get the first question. Okay.
Yeah, you always do.
That's true. I want to establish a sort of broad base from the first book, which I have back here, but you can't see it. So here I'm holding up Magnitude, which is a very lovely book, as we've seen from, I have to remember, from this press, I don't have the right glasses on to read, that it's from Black Dog and Leventhal Publishers, who put out very nice books. And I want to clarify and then get an idea from you how you came about what the idea of magnitude is here. We're not talking about magnitude as just big things, as you might say, oh, such magnitude. But we're talking about magnitude as an idea that's very familiar to me as a physicist, that relates to things that can be measured, and then relating that to the universe. So tell us about magnitude, why you're doing it, and what magnitude really means.
I can go ahead and start, and Kim can jump in if she wants. So magnitude means a lot of things. Obviously in sort of everyday language, it means, heaviness or weight or importance. But what we mean here is in sort of a scientific, mathematical sense, and that means being able to compare the size or the amount of something to something else. And the concept really came partly from our day job where we are constantly talking about things that are really large, things that are really massive, things that are really hot. And we had to explain them in a way that is relatable. And often things in space are at some extreme end of a range. And so how do you really make that relevant for a non-expert? So, we are very much both big fans of the powers of 10. And that was one amazing way to sort of simply depict the range of physical size. Back in the day, I think Kim said yesterday, it's 40 years ago this year, that movie came out, or a version came out. Anyhow, Excuse me. So what we wanted to do with this book was to show that there's this amazing range, not just on physical size, but on multiple physical phenomena, speed, pressure, rotation. There's, I can't remember the exact number, 13 or 14 different topics that we like to, share and explore that range of magnitude in each and every one of those. So it sort of starts with our day job and explaining the amazing things that space sort of, can, shows examples, but it really, there's so many examples throughout our daily lives too. That's also the impetus to come up with a book like this.
Yeah, exactly. So as Megan mentioned, we've been working for the Chandrix Observatory for a long time. So Megan and I have been working together for a while. And that means we've fielded a lot of questions from the public at events and talks, through emails, through social media. And one of the biggest questions that's always on repeat is this idea of scale and magnitude. How big is this? How dense is this? How fast is it? Like, what are these sizes and how do we relate to them? And we've done a little bit of research on that as well through the Astronomy and Aesthetics project that kind of tries to figure out how both experts and non-experts look at different kinds of scientific objects, mostly astronomical, but also others, and then how they're able to comprehend different issues of scale and what questions they have. So this book felt kind of like a natural extension from those questions and those issues that we're constantly having to grapple with. Because you can talk about something being, 30 light years across, but what does that mean? And as she mentioned, a major reference point for us has been that Powers of 10 movie. And it was such a beautifully done video at the time, 40 years ago this year. Yeah. And to be able to take that and expand it into different subject matter. So it's not just the distance scale, but also, as Megan mentioned, whether it's pressure, density, area, and try to make that relatable to things we can, grasp a little bit more firmly down here on Earth.
In a previous life, I worked on a space shuttle experiment that did a physics experiment on orbit. And our particular experiment was critical phenomena, and we dealt with things like microkelvins and microgravity and all of these things. And so I see now, obviously, the connections. Like, you've been public affairs, science outreach people with Chandra, and the two questions I think that always came up when we were trying to talk to people and prepare statements about our experiment was, one, what's it good for? That takes a long time to figure out, but it's certainly worth knowing to tell taxpayers who are paying the bill. And the other one was, well, how big is that really? What can you relate that to? It's like, so suddenly I see, it's like, I can imagine exactly where that question came from. And so magnitude here struck me as two things, both of which are so far back that I don't remember having to learn them, but I think people find difficult to grapple with. And the one is the idea is like all these things that can be measured that you're talking about. You're talking about distance, you're talking about surface area, volume, acceleration, mass, and pretty much all the things that seem to be oddly central to physics. Like, this is all the stuff that I learned about it the very first time in physics. But then also this problem of orders of magnitude. An amazing thing that becomes everyday shorthand in my scientific community. But what does orders of magnitude mean is a really exciting thing to get at. And then trying somehow to relate things that are a gazillion times bigger than these things that are a billion times smaller than that when it comes to looking at their distance from us, their weight, their mass, their length, and things. Okay, now I'm rambling.
Well, I noticed something. I noticed that when you could, you sort of repeated a structure or a concept in each, each dimension or each concept, right? So if, red blood cells kept appearing through, so whether you talked about size or area or, velocity or, all these things were repeated. And I certainly felt that was intentional.
Yeah, and actually, we weren't sure if that would seem odd at first, and we talked about it with our editor because we repeated supernova remnants a lot. So we both work pretty heavily with data on supernova remnants. Obviously, because of our day job, the Tanner's Observatory takes unparalleled images of exploded stars and X-ray light, and I think our department does a really good job of helping to visualize those specific objects in these beautiful ways. But they can be still really difficult to talk about and to translate into scales that can be understood. So I think repeated Cassiopeia A as one specific example of a supernova remnant a couple times, and I think we had another supernova remnant in there as well that felt useful to us because you can talk about the area of a supernova remnant, and that's one thing, but you can also talk about the energy output, and that's something totally different. But when you can kind of get some of these pieces of the same type of object and then still keep relating them to other types of things, it's, I think, really helpful for that idea of relevance and being able to relate to them. With Cassiopeia A, I talk about it like nonstop, as Megan knows. She's probably sick of hearing me bring it up as an example, because like every talk I give, every possible thing I write about, it's always Cassie. It's this beautiful star that exploded many times the size of our sun. It's collapsed, ran out of energy, then exploded all over the place. So when we're looking at an object like that and we talk about how much area it might take up, now it's been expanding for 10,000 plus years. So it's, really quite big right now. And if you say, if you're looking at an image of Cassiopeia A and it's 30 light years across, all right, a light year is about 10 trillion kilometers. So you kind of can get a sense of that, but still, what does that mean? And then when you kind of extrapolate it down to the fact that the area of Cassiopeia A is about 40 million billion times the surface area of our star, and you can toss in the other 8 planets because they don't really matter at that scale, but that size difference is really interesting to be able to relate to. And the same thing when you talk about its energy output, or even our other book on light, I think we talked about the idea of atomic collisions in that one, and how you can relate that, something's going on in this beautiful pulsar and it's very far away, 25,000 light years or more, but something very similar happens in a neon sign that you see at the diner. So when you can get those kind of extrapolations and understand that there is a similar process going on here, it just gives you another, frame of reference for your own interaction with that information.
Yeah, so I think just to build on what Kim said, I think if there is a common thread of all the things that we've done in our careers as have gone on, I think it's trying to make people understand or convince them that science isn't some other thing that happens with a small segment of people. Science is all around us, and it's something that everyone can appreciate and should hopefully feel not scared of or intimidated by, because I feel like what we're trying to do is to sort of make those connections between maybe something that seems like something totally foreign and esoteric, like whether it's a supernova remnant. We want to make sure people understand that those same physical processes affect them in their daily lives, and also that these concepts are things that they can understand. It's just you need to have it explained well to you. It's not that there are science people and non-science people. It's that there's sort of poor explanations and good explanations, good teachers, bad teachers, whatever. So that's one of the overarching big picture goals I think for our books is to make those connections for people, so that people understand that science is all around us, and they can learn that the scientific process isn't something foreign or weird, or especially I think in this day and age we really need to work on making maybe not scientific literacy such a priority, maybe even just scientific receptivity. People are not so scared of science, and these books are one of our small steps to try to do that, I think, is because we feel like it's so important for people to feel comfortable with science.
So I want to just show this page. There's a lot of, all the pages are great, but yeah.
I know that Labrador.
I know, this Labrador just caught my eye. So yay, props to your illustrator. But we start with the electron to DNA to a human eyelash, which, not many people are thinking, oh, that has some mass, doesn't it? And yeah, to the dog, to the Hubble. And yeah, as we go on, we've got the blue whale, I think.
Yes.
Can't turn the page, but yes. the blue whale, Halley's Comet. And I felt like, that's right. I don't sit around and say, oh, Halley's Comet has mass, but of course I know it does. I took physics, the Earth, and we've got a black hole and a galaxy cluster. And I felt it was really wonderful the way you go from very small to very big, or very slow to very fast. Everything it scales up.
Yeah, and you talked about you mentioned the illustrations too, and that was another thing that we've never done before this book is to have a whole book of illustrations. I'm a data person, so I'm usually like images, data, great. But with this topic, it really made sense to think about it differently, and I think the infographics provide a really nice continual visual that helps ground the whole book. In this idea of cohesiveness and relevance. The illustrator that our editor hooked us up with, Katie Peak, is an astrophysicist. So it was just like a perfect partnership to be able to get all of these topics illustrated so well to kind of help get those concepts across,
Right. Yes, exactly. How do you do the mass density of the universe,
Right. Exactly.
It's amazing.
Especially when we get down to the really small sizes, you can't really image that stuff directly. Or when you talk about things like black holes, you can't image that directly. So there was a lot in this book that I think it made sense to take this different visualization approach through these infographics. And I just love the way they came out. Like it feels very like it's telling a very visual story. And I definitely appreciated the way Katie was able to do that so beautifully.
Well, as I was reading through the book, after we received our copies, I was thinking, I want to give this to our school physics teacher. I have a feeling he would love to have that in his library at school. And I have this feeling like at the holidays when this book is on the coffee table, people will be pouring through it because it's lovely and it displays concepts. And my kids are very physics minded, so I think they're going to love it.
Great.
I'm always happy to hear that. How foreign is the idea that physics works the same in distant galaxies as it does inside the human body? This is another thing that we insist, from the beginning, and the excitement of Newton's universal law of gravitation was realizing that gravity is something that makes the apple fall on his head, but it's also the thing that keeps the moon in orbit. And it's easy for me to forget that was a great new idea and a unifying element that physics and then chemistry and then we assume that they appear to work the same every place and at every scale. That really is a pretty remarkable thing.
Yeah, I think, it depends on who you ask, right? If you talk to a scientist, they'll say, of course, right? That's sort of a given. Am I frozen or is just Jeff frozen?
You're fine.
Oh, okay, sorry. I wasn't sure. It looked like there was a technical difficulty. So I feel like the concept of sort of this universality of science is not as well known as those of us who work in science think it is. I think people feel, especially since there's so much pseudoscience out there, I think there's this sort of, unfortunately, a sort of in certain segments of the population, there's a lack of understanding about how science works, and that the processes we're talking about for something that's either inside the body or on a microscopic scale or on a cosmic scale can have the same physics and underlying processes and rules and laws as do the things that you see walking down the street. And that's how our world works. I mean, we take science is so embedded into our society and our lives. I mean, even just looking at your cell phone, I mean, how does that work? It works based on the understanding of, lots of different science, including a little bit of relativity thrown in there with, for GPS and all sorts of things. So I think that understanding that science is not some quote other entity, but it's just part of our lives on a micro and on a daily and on a macro scale is not as well recognized as I think science people might think it is. So that's one of the reasons why we try to always tie the exotic or the unusual or the exciting science back down to sort of, relatable ways for everyday experience to show that they're not fundamentally different. They're just really cool examples of an extreme or something that maybe you don't see every day, but it's connected to your everyday experience, if that makes sense.
And I feel like that idea, like this holistic approach to science, I guess to use that term, is something that we've done for sure in our day job. We've been trying to do that as much as we can. The Tandark Observatory is, high energy astrophysics. It's looking at some really esoteric things, black holes, dark matter, not always so graspable. So I think it's been a challenge that we've had in our day job to be able to talk about some of these topics in a way that is more relatable. And we've tried to bring some of that to our books. I think the last 2 books in particular, we've done that the most because the topics kind of let us branch out, right? Exactly. Light, that Joanne's beautifully showing right now, and also magnitude too. Because you can talk about some of the most simple concepts and really learn a lot about them. Like, I was at a beach with my kids and niece a number of years ago, and I took this photo of their shadows on the beach. And I loved that photo because visually it was beautiful, right? But then I'm like, shadows, those are kind of interesting. And the more you think about them, the more interesting it becomes. All right, blocked light. All right, let's think about blocked light, And do we really use the idea of shadows in science? Oh, we sure do. I mean, you can look at astronomy alone, and the idea of blocked light has helped this huge explosion of discoveries around exoplanets, And so now we've learned about thousands of these exoplanets. And we find out things like, it's raining diamonds on one of them, and it's raining sapphires and rubies on another. No big deal. So, I mean, the idea that just a simple concept of blocked light was the impetus that led to some of those other discoveries. I mean, they took spectroscopy and other stuff to figure out some of the details, but it was that basic underlying theme. So simple, the shadow. And what can that do for us in science? Well, it can do a lot. So yeah, that's something that I think we've been trying to bring out in our books just as a way to look at some of these really basic things that have a huge impact on what we know about the world around us.
So, and actually for those of you who don't have light, when did this come out? Was it just a few years ago, maybe 3 years ago?
2 years ago, 2015.
2 years, yeah.
Okay. So yeah, it just seems like I just got it, but I've had it. So those of you who aren't familiar with their book, it starts at one end of the wavelength spectrum and moves to the other end, much as this magnitude does. I thought that was a clever way to set this up. Is this the same illustrator, or it seems like you have a lot of images?
Those are all images. Yeah.
Those are almost all data-based images in that book, and that's my specialty. I do love data, as I mentioned. Right. So it was a pure pleasure to hunt down those images because there are just so many beautiful photographs, microscopic images, astronomical images.
And a lot of these are from NASA, so they're sort of public use.
Yep, yes. Exactly. And we have fortunately grown a nice network of friends who are scientists, who are photographers, who we've been able to rely on for other projects. And they're all so gracious in letting us use their imagery in exchange for a couple copies of the book or whatever. So it was a really fun book to work on.
Because of course, any book like this, images are very pricey. So
yes, exactly. Yeah.
We all know this photo, hopefully.
Yeah.
Yeah, I mean, that book was really almost a direct extension of our day job, which is, if you work for Chandra, which is an X-ray telescope, the first question you have to ask or answer often is, what is an X-ray? Why do you, and also the second question is, why do you care about them? Why do you need another kind of telescope if you've got Hubble? There's a lot of these. And then that is a natural discussion of, well, there actually are many different kinds of light in addition to what we see with our eyes. And that simple concept alone is something that I don't think a lot of people outside of science understand, that there's different kinds of light. So really, it was just a sort of a labor of love, to be able to explore that and explain it and, find the coolest little facts about each kind of light and share that. And so that was a really fun project. And we have X-rays in there for Chandra, but, it was the whole, as working in astronomy, so many times we have multi-wavelength images where we have different pieces of, the spectrum that we overlay together to tell the more complete picture. It's sort of like pieces of a puzzle. even though people, and I don't think people fully, even though they love these images that they see, sometimes they don't know that they're seeing different kinds of light. And it sort of gets back to what Kim was talking about earlier. There's representation of data, different issues of color. How do you see something that's invisible? How do you make an image of something out of something that you cannot possibly see with the naked eye? So it's just a lot of stuff. It was fun to make. And, I think it's a fascinating topic. And again, one where there are examples in every wavelength that affect our daily lives that most people use daily, and they might not even realize it. So that was fun.
Right. This picture really caught my eye, because here's the things we use in our lives down below that fall on the different wavelengths. But then also these are some of the imaging satellites that are out there. Well, maybe not. That's not a satellite, but I thought, wow, that encapsulated it so nicely.
Yeah, and that's the sort of thing. I use that image or a version of that image to talk about this idea of the multi-wavelength universe a lot, because it's such a simple way to be able to connect these types of light with things that people already know and have experience with. If you're using a microwave to heat up that macaroni and cheese, if you're using your infrared on remote control, if you're getting x-rays at the dentist, I mean, just having a general familiarity with those different kinds of light. I think not everybody even realizes that they do. If you're a comic book fan, you think of the Hulk and how the Hulk got to be the Hulk. There are all these different kinds of light that are kind of there in our daily world already. So just putting a name to those things that you're already, familiar with, I think is quite useful.
Right.
It extends that universality theme that you see in magnitude of, yes, there are different kinds of light. Yes, these are all light. Yes, they are all electromagnetic waves. And so at some fundamental level, they're very similar, and you can understand them as different things, and you can understand them as the same thing.
Exactly.
It's really, really good. So these two books are very, Light and Magnitude are very visual books. And so was this, your Ticket to the Universe. So this was your first book?
Yes.
Sorry about the cover. It should be brighter.
Yeah. Yeah, so it's actually kind of, I don't know, Megan, I like this story. Maybe it's dorky, but so Megan and I never really had some grand plan to write books together. Like it wasn't something that we thought, oh, let's go write books, We write a lot of articles together for a day job, and I think we've both enjoyed writing creatively on the side in addition as well. And a literary agent, Elizabeth Evans, had actually seen an article we wrote together for, I think it was the International Year of Astronomy back in 2009. And she actually approached us and thought, have you guys considered writing a book?